Presentation is about a bulletproof hoster named Fluxxy. Fluxxy is actually a botnet, a fast flux botnet that supports that bulletproof hosting. But first thing first, um, I'm part of the technical collection and research team at Mandiant Intelligence. What we do is we collect raw intelligence directly from adversary infrastructure. One of our main way to do that is to emulate botnets. So we reverse botnets, create emulators, and use those emulators to either collect information from command and controls or directly from the botnet. What kind of information we collect from that? Obviously, we get indicators, high confidence indicators, because when you have an emulator that uses the botnet protocol and successfully connect to a server using that protocol, that means that that server is definitely related to that botnet. Also, we get things like web injects. So web injects are small scripts that are injected into browsers to collect user credentials. And those scripts also use what we call ATS that are secondary controllers to which the intercepted credentials are sent to. For spam bots, what we get obviously are spam templates. That is, whenever a new spam campaign is pushed to the bots, usually received a spam template. That is a template to generate emails to send over for the campaign. For other kind of botnets where the owner sells some part of the botnet, that could be a compromised machine. Actually, what it does, it sells access. And for that kind of botnet, what we see is usually secondary payloads. For example, when the owner of the botnet sells a bot to another actor, that actor might deploy a stealer, recon tool, or ransomware, stuff like that. This is the kind of activity we can detect via botnet emulation. We also have some dedicated trackers, for example, for bulletproof hoster, because bulletproof hoster are interesting for us. Many botnets use controllers behind bulletproof hoster. And that sometimes blurs the lines between the different actors. And if you can track the bulletproof hoster and the infrastructure behind, you are able to do a better breakdown over the different actors within the different botnets. So to do that, we support about 60 families. The most famous one are Emotet, Trickbot, Catbot, Selenite. So yeah, about 60. So what about Flux? So Fluxxy is a fast flux botnet that is used as a protection layer to hide the backends. So it does both DNS service, that is resolving domain names to IPs to that protection layer, and content delivery. That is, once that domain name must be resolved to the protection layer acts as a proxy between the backend that is hidden and the customer or the client. So that's a real business. We know about two actors selling the Fluxxy service on the underground. One is CCWeb. CCWeb sells directly the protection layer. That is, provides you with a panel to configure your backend and the domain names you want to point to that backend, and it tells you that service where the protection layer would be configured between the backend and that domain name. Sol hosts provide a similar service, but directly VPS that is already configured behind that protection layer. Actually, we don't know if CCWeb and Sol hosts are two handles for the same actor, but we definitely know that both are selling the service associated to Fluxxy. That amount of money for a bulletproof hoster is pretty high compared to competitors such as Yalishinda, Brothers. Thing is, Fluxxy really seek for high-end customers, like customers that can pay that amount of money. For example, we saw GunCrab when it was still active, 9mm, Fin11 distribution, many carding forums, that is for marketplaces where you can buy stolen credit cards or stolen access, stolen credentials. Obviously, for that kind of business, you want to hide your backend. So this summarizes what I explained. That is, when you want to access a server that is hosted on Fluxxy, first thing, you resolve a domain name that is associated to that server. You resolve that domain name over public DNS. Obviously, the public DNS, such as Quad 8, Quad 1, would forward the request to the associated name server. That name server is actually hosted on Fluxxy. Fluxxy would reply with a dozen IP addresses that point back to the Fluxxy botnet. Then, for example, if you do HTTP, you would contact that IP address with the associated host, and the Fluxxy node would forward the request to a backend and act as a proxy between the client and the backend. So it's a fast Flux botnet because the IP that are provided by a botnet for the domain name change about every 15 minutes. And that's the same for the name, the associated name server. Actually, there is a secondary botnet that is named 13. There are few analyses about the 13 malware. So 13 is actually just a loader that, and the 13 botnet acts as an infection pool for Fluxxy. So whenever the operators want to replace a Fluxxy node because it is bugging or because it got infected, they select the 13 node, check it's legit, running a few tests on it, and promote it to Fluxxy. That is loading the Fluxxy binary and mapping the bot ID to production network. We know that both networks are related because they share controllers. So pretty good indicator to tell that both networks are related. So what we want to do is to collect information from the adversary infrastructure here. So the first thing to do that is to understand how the Fluxxy networks communicate with its controller. So Fluxxy use what we name DNS beacon. That is, you take the message you want to send to a controller, you encode that into a domain, you append that domain to a master domain, and you send that big domain for resolution over public DNS. Obviously, the public DNS infrastructure will forward that domain name to the associated name server, and the Fluxxy operators typically control either the associated name server or control a gateway between the public DNS exits and the configured name server. So this is not new technology. There are many malwares that use that kind of beacon. However, when a malware uses that kind of technology, usually the DNS beacon, that is the domain names, end up on passive DNS databases. And Fluxxy operators know that. So they don't want their beacon to be logged into passive DNS. So what they do is that on all DNS requests, they reply with a server fail. And that's a message that tells you that the DNS query resolution just failed because the server did not answer. So that's usually enough for to prevent DNS resolution requests to be logged in passive DNS. But back in 2013, there was an outage that and several public DNS servers were failing and resolved all domain names to the same IP address. This was documented on TechNet. And one of the Fluxxy master was part of that outage. So for a short period of time, all DNS requests to that master actually resolved to a valid IP address, and the DNS resolution ended up on passive DNS databases. So that's an example of Fluxxy beacon you can find on passive DNS. So that big domain with the random part at the beginning is actually the message, and the last part, masters.bulklabs.com, is a master, a Fluxxy master domain. So now we have that beacon, and what we want to do is to decode it. So that's where it gets a bit more difficult. Fluxxy binaries use a library, a C++ library that is named CryptoPP. It's a library where all public key algorithms are encoded or with the same template. It is all coded with the same template. RSA, elliptic curve, ElGamal, all those public algorithms are encoded with the same template because they most of them relies on the same primitive. The same cryptographic primitive. And what changed is how you do an addition, how you do an exponentiation, how you do that kind of thing. And so that to reverse that kind of code when all symbols are stripped, you really need to know how the different algorithm works. So yeah, I made it for Fluxxy, and I was able to identify that Fluxxy used ElGamal. So ElGamal is a pretty simple algorithm. So the idea is that you have a field generated by a prime and generator. So here it's 3. Your public key is just a number in that field that you exponentiate. That is, you take 3 and you exponentiate 3 with your private key. You obtain a public key, and you use that public key to encrypt the messages. So obviously, it is difficult to compute the private key from the public key because discrete logarithm is a difficult operation. However, you can notice that public key is pretty small, and if you have the right tooling, such as KDONFS, you can actually compute the logarithm and obtain the private key. So this is what I did here. So KDONFS is pretty simple to use. You use a DLP option, put that big number, and it will compute a discrete logarithm. However, and this is a principle of the field seeding, you don't know which base that logarithm is computed from. It can be any base. And what we want is the logarithm on base 3, 3 being the generator of the field. So once you have the result from KDONFS, you just need to divide that result by the log3 logarithm that is also provided by KDONFS. So that's those few lines of Python show how to compute that final logarithm, and you obtain that private key 58645, so on. So once you have that private key, you can decode that message. You just need to decrypt with ElGamal with the provided private key, and what you get is protocol version. Here it's 1. The current protocol version is 12. the node IP, that is the IP address of the victim machine. A few flags that tells you if the machine is a VM, if it is stage 1 loaded. Stage 1 is the 13 binary I told you about before, and if it has firewall activated or not. Then you get the uptime. The uptime is used to select the nodes that are put into production. If you have an uptime that is too short, you in staging until your uptime grow enough to know that the machine is reliable enough to be put in production. And finally, the bot ID. So that's the really important part. So I told you about that selection process where you have first team node promoted to Fluxxy. When they do that promotion, they record the bot ID as part of the production network, the Fluxxy production network. And if you beacon with a random bot ID that you generated randomly, you won't get any reply. You won't get any config. You won't get any into the network actually. You really need to use a bot ID that has been selected to be able to receive configuration from the Fluxxy network. So this is why being able to intercept first those beacons and to be able to decrypt those beacons is really important when you want to collect information from the botnet. So what I just presented was actually the Fluxxy protocol until end 2019. In 2019, they released a new binary that I named Fluxxy FFP. FFP being a reference in the Fluxxy binary, and it stands for Fast Flux Proxy. When that deployment of that new version of Fluxxy happened, a couple of researchers noticed that and thought that a new fast flux botnet was emerging. Actually, and one of the name Catherine gave was SandyFlex. And actually, it's really the same botnet. It's just Fluxxy, where new binary were deployed, and since those binary features new capabilities, so resulting botnet looked a bit different. So again, what you have to do when you track adversary infrastructure and there's new deployment of a binary, you need to reverse it and to understand again the protocol. So what they did here is that really improve that enrollment process. I told you about that 13 part where they're promoted nodes to Fluxxy, and now they have additional checks on once in production. So that new protocol don't use DNS beacon anymore. What they do is first they check a master domain here, assassin.mo.com, and fetch the associated TXT record. So TXT record is just a text associated to a domain name and stored on public DNS infrastructures. And that TXT record is actually an RSA signature. And the binary include a hard-coded public key. And if that signature match the RSA public key, then go to the padding data. Decode it further. There is an additional RSA there. And interpret the resulting data as IP addresses. So, for example, on the 512 RSA signature, you have about 12 bytes of binding data. So once you have decoded the padding data into an IP address, you take your beacon message, you encrypt it with elliptic curve, again, publicly as coded in the sample, and you send that beacon blindly on any UDP port or any ICMP ID associated to that IP address. And you do that blind. That is, you send the backend and that's all. You don't expect any reply. you don't even know if the packet reached the IP address. But if you do that correctly, and if you pass a few checks, they'll do on the node, you'll receive a new config with new master domain, new crypto keys, new DGA seeds, a whole new configuration. And you do that again. That is, you have a new master, you fetch a TXT record, go to the padding data, decode the padding data, get IP addresses, and again, do blind beacons to those IP addresses or UDP ICMP. In the meantime, so say no control node with that staging configuration, and they will test the node. They will test the boundwise. They will test the running processes. They will test the attached devices. So that they're sure that that node can be put into production. It is legit. It is okay to use. So if you pass all those stages, all those tests, and if you do the beaconing correctly, at some point you would receive a final production configuration from the Fluxxy network. And this is how you know that binary is completely related to Fluxxy, because the source of the config would be a Fluxxy subnetwork. Well, this is, for example, the RSA signature that is associated to assassin.mu.com, and the RSA public key, that is the modulus. Actually, that modulus is weak. That is, you can factor it into 2 primes. That fact will be important for what's coming next. So now, what's interesting with that new version of Fluxxy is the ways they manage bots. So you can push configuration to a bot that would include crypto keys. There's master domains, DGA configuration, SSL certificates, because the node will act as a proxy for content delivery, and that can be over SSL. And you can also push new binaries or send commands, but those need to be signed with much larger RSA key. I believe, if I remember correctly, it's 2048 bits key. So that one, I won't be able to crack. But anyway, but what's interesting there is that all that configuration you can push to a node, you cannot read it back. That is, by design, the Fluxxy developer made it difficult to read back the configuration of a node, so that they know that if they push configuration to a node themselves, they cannot read it back. So they know that security researcher won't be able to read information, those interesting information from a node. However, what you can do, what you can read from a node are running process names, telemetry data to check that the node is okay, attached devices to check that the node is legit and not, security researcher virtual machine. Some statistics and telemetry on the inbound data, that is what IP addresses were client for content delivery or DNS requests. And a bug check. That's that bug check. You just send a message, and the Fluxxy binary would take a memory dump of its own process and send that memory dump to the controller. The controller being the IP address that was decoded from the RSA signature in the binding data. So if you control signature, you would be able to encode an IP address there. And if you trigger a bug check, then you can get a memory dump and read the node configuration. So yeah, it's not easy, but that's the way. Another interesting point with Fluxxy is its DNS server. because it's completely custom. For example, it supports a subset of DNS records. It has some auto-tuning capabilities. That is, typically a subdomain would raise up to the same IP as the master domain. If you take a.a.a.a.Fluxxy domain, you would get the same IP addresses as the Fluxxy domain. So this is not usual behavior for a DNS server, and this is a way to identify Fluxxy domains. Similarly, the SOA is auto-generated on the requested domain. So if you do a.a.a.a, you get an SOA generated on that big domain, which is completely unusual. So it's a really good way to fingerprint DNS infrastructure supported by Fluxxy or DNS domains, or the Fluxxy DNS domains. Another interesting feature is they can implement whitelist and blacklist on the DNS server. So if you're blacklisted, the DNS server won't reply to your DNS requests. Also, they have a masquerade list. That is, if you are on the masquerade list, the DNS would reply with other IP addresses, that decoy IP addresses. I'm not sure how they use that, but yeah, my belief is that they use that to, to blur lines and to make security companies or security researchers think that the domain is legit, because it doesn't resort to bad IP addresses. Finally, there is a default domain that is configured on all nodes, and that domain is derived from the bot ID. So if you have the bot ID, you can check that the node is actually live and a Fluxxy node. All those can be used to fingerprint Fluxxy nodes. Also, Fluxxy does content delivery, and that's an example of a configuration of a content delivery. So I believe that was a configuration for Dreambot. So all those domains used as host for HTTP proxy would be, and the data would be forwarded to that IP address on port 80. That mapping, that proxy mapping, is associated to blacklist. They also use blacklist and whitelist for content delivery. And what you can see, TCP BL hash is actually the hash of the blacklist. And to get the actual blacklist, you need to query a peer Fluxxy node for the blacklist with the hash. And also that mapping is actually bound to SSL, and the SSL session is ended on the Fluxxy node. That's interesting because the traffic between the node and the backend is actually in clear text, and the node receives the certificate and the private key for the certificate to do the SSL termination. But this is just an example. They also have other configuration where the traffic is actually encrypted end to end and not point to point like this one. They have that protocol that actually looks like Tor protocol, when they can encrypt the traffic at the entry node and decrypt the traffic at the exit node, and in the middle the traffic is encrypted. So if you control the exit node, you would be able to see the reply in clear text, and if you control the entry node, you can see the query in clear text, which is actually the same as Tor. If you control exit or exit nodes, you can see some part of the traffic. And that's all for today, and I hope you liked the presentation. If you have any questions, I'm happy to answer them.